I want to talk about partial fractions. This is something I alluded to last time. The partial fractions. This is a trick which actually is not only for doing integrals, but integrals is one thing that partial fractions can help out with. Maybe we should just try to actually do the example that I discussed last time was, I believe, this. I think that was it. Yeah. Doing the partial fractions on this. The purpose of the partial fractions, at least for our purposes, is being able to do the integral. But the partial fractions in general is a trick where you can start with a function that looks like this. That is to say, a fraction with a polynomial in the denominator. And you can split it up as something over, well, let me just say, first you factor. This one factors as x minus 4 and x plus 1. And the point of the partial fractions trick is to split it up into two fractions like this, with some constant numerator terms here. So I'm going to call these, let's say, A and B. Now, if you look back at your notes from last time, it turns out in this example, A is 1/5 and B is -1/5, something like that, maybe the other way around. Let's talk about how you could actually calculate those. All right, our goal here is to solve for A and B. And this is called the partial fractions decomposition. We want to figure out what the A and the B are. And the way we can do that is simplify that thing on the right-hand side. We can actually add the fractions with a common denominator. So from here, I am going to do a common denominator and add. Now, our common denominator in this case must just be the product of those two denominators because they don't have common factors or anything like that. So our common denominator will be this, all right? And the first one, in order to get that denominator, you have to multiply by x plus 1 on the top and the bottom. So it'll say A, x plus 1. Come on, buddy. Right? And then the other one, we have to multiply by x minus 4. So the other one will say B, x minus 4. And then that same denominator. All right? My intention is to actually add them together with the common denominator. Okay, and here I would distribute the A and the B in the numerators there and then add them up. So these, when you actually add them, we have the same denominator, but the numerator is whatever the sum of those two numerators are, and I'm going to distribute the A, so it'll say AX plus A from the first one, and distribute the B on the second one, BX minus 4B. All right? And maybe I'll write this all the way across. Remember, this all began over here. So this thing right there is supposed to be equal to 1 over that thing on the denominator, which of course is the same denominator as you see on the right-hand side. It's just factored or not. All right? And here is where we're going to be able to solve for the A and the B, kinda, at least. These are two fractions. Their denominators are the same. They don't look exactly the same, but they are if you expand the one on the right. So we can set their numerators equal to one another, like they're the same fraction, so the numerators have to be equal. So the numerator is 1 on the left side, and on the right side, I'm going to regroup things in terms of which ones are coefficients on x. So I have an ax and also a bx. AX and a BX, and then I have an A and a minus 4B, right? Just sort of grouping together the x parts and the constant parts. And just to be extra suggestive here, I'm going to write it as A plus B x plus A minus 4B equals 0x plus 1. I wrote them in the other, I switched around the two sides, but this over here, I just factored x out of the first two. And then over here, I just wrote 1 again, but I wrote 0 times x plus 1. That's because I am thinking of both sides here as being polynomials of degree 1, all right? They have a constant part, and also an x part. Now this one here just happens to have their x part has a 0 coefficient, all right? But anyway, now we can equate the like terms, as they say. That is, there's an x term on the left and an x term on the right, and those must be equal because these are, either side of the equal sign are two polynomials of degree 1. That means their degree 1's coefficients has to be equal, and also their constants have to be equal. So from the left side, I get a plus b equals 0. That's the x terms. I'm equating the coefficients on x on either side. And then we also have equating the constants on either side. The left side is a minus 4b, and the right side is just 1. And here, finally, we can solve for a and b. This is a linear system in 2 variables and 2 equations, so we should be able to solve the system for a and b. I'm sure you learned several methods for doing this. Usually I would do substitutions, right? You could solve the first one for a and then plug that into the second one and so on, right? You could also add and subtract the equations from one another. I don't know if you like that. Let's try that. This one, if I were to subtract the second equation from the first, I'm doing the first equation minus the second one. The a's would cancel, which is good. And then I would get b minus negative 4b. That's 5b. And on the right-hand side, 0 minus 1 is negative 1. So b is minus a fifth. You could do this by doing substitutions if you prefer that way. All right. And then what about a? Then we sort of plug back in here. This will say a equals 0 minus b, right? And if b is negative a fifth, that means negative a fifth. It's positive a fifth. All right, so these are my constants. This is how you do the partial fractions thing. These are the constants that I just sort of told you to take my word for it last time. But this is how you solve for them. All right, so in conclusion, why do we care about all of this? It's really because we want to do this integral. And the idea is that integral is actually the same as a over, it's this, right? These two fractions with those a's and b's. So it's a over x minus 4, which is 1/5 over x minus 4, and then plus another integral, negative a fifth over x plus 1. All right, that's the partial fractions decomposition of the thing we started with. And this now, we can do, those integrals are both easy to do. They're just a natural log with those constants up top. You can just pull them out of the integral. And so this one is 1/5 natural log x minus 4. And then this one is negative a fifth ln x plus 1, like so. All right, that's the partial fractions trick. That's how we do it. Any questions about that one? There's not a whole lot to it. Let's just try one more, and then I got one for you to try. See how we do. Let's try integral 5x minus 16 over x squared minus 7x plus 10. All right. Same deal. We are going to do the partial fractions. So let's just sort of forget about the integral at this point. I mean, the integral is like the easiest part. The more involved part is actually figuring out what those fractions are. So it's gonna be 5x minus 16. Let's factor on the bottom. Can somebody say what are the factors on the bottom? Shout them out. Yeah. Yes, I agree. X minus 2 and x minus 5. Great. So I need to write this as something over x minus 2 and another something over x minus 5. That's the idea. This is always the goal of the partial fractions decomposition. All right. And how we do it? We actually add those two things on the right-hand side together with the common denominator. All right. The common denominator, of course, will be x minus 2 times x minus 5. And to get there, the first fraction we have to multiply by x minus 5. So this will be like so. And the second one we have to multiply by x minus 2. So it's b x minus 2 over the same thing. All right. Combine them together into one fraction. They already have the same denominator, so we're just going to add the numerators. And those numerators, I will distribute the a's and the b's. So it'll say ax minus 5a plus bx minus 2b over that same stuff. All right, the denominator is not really very important because, remember, we are going to equate this numerator at the end with the original numerator that we started with. So it'll say 5x minus 16 equals all of that business over here. And I'm going to rearrange, group the x terms together, group the constant terms together. So the x terms are a plus b x, and the constant terms are negative 5a minus 2b. Right. And then finally, we equate the like terms, right? The x coefficient on the left is a 5. The x coefficient on the right is a plus b. So a plus b is 5. And for the same reason, minus 5a minus 2b is negative 16. And then this here is the system which we shall solve. Maybe I'll do this one by substitutions. So if I solve the top equation for a, it says a equals 5 minus b, and then plug that into the second equation, it'll say negative 5 minus b, minus 2b is minus 16, right? This is not, I would say this is not difficult. You just got to make sure you don't mess it up. Like, it is easy to make little mistakes as you're doing all of this. Distribute the 5 here, minus 25 plus 5b minus 2b is negative 16. Add 25, that will be 9 on the right side, and then 5 minus 2b is 3b. So I think b is 3. Anybody agree? I think so. All right. And then what's A? A, I already set up there. A is 5 minus b. So A is 5 minus 3, which is 2. And this is our, well, those are the coefficients at least on our partial fractions decomposition, right? So up here, if you want to do the integral of the thing on the left, it's the same as the integral of these two things added together. And we now know what the a's and the b's are. So my original integral, 5x minus 16, x squared minus 7x plus 10. This is equal to integral of, a was 2 over x minus 2, and 3 is the other one, over x minus 5. Make sure you put the a and the b in the proper spots, but I think I did. Right, and now we just do the integral. Factor the numerators out. 2 ln x minus 2 is the first integral. And then 3 ln x minus 5. There you go. That's what I say. Right, this is the partial fractions decomposition trick for doing the integral. All right, I got one for you. See how you like it, how you like me now. Try this here. 3x plus 31, x squared minus 5x minus 24. See what you think. That's a minus 5x there. free to talk to your neighbors if you like. I'm going to start writing my answer up here. People seem all right. All right, can we talk about it? People seem, I think, you are just as good at doing this as I am. It's just a lot of sort of multiplying and adding without making mistakes. Hopefully it's not so bad. This is where I started off. I did a couple of steps in my head, which is fine with me if you want to. This is what you'll get when you add them together with the common denominators. And then distributing the A and the B gives you this in the numerators, which gives me these two for the system. Now, if you had arranged your A's and B's the other way around, it might look different, but I got A plus B is 3, and then minus 8A plus 3B is 31. And then to solve the system, I thought I was feeling cute, so I decided to add the equations. I'm going to add 8 times the top equation to the second one. This will cancel the A's, and then here it'll be 8B plus 3B shall be 11B, and on the right-hand side, 8 times 3 is 24, plus 31 is 55, and then solving for B gives me B equals 5. You could solve this, of course, many ways, doing substitutions or whatever. And then, so if B is 5, then the A plus 5 is 3, so A is negative 2. All right. If you set your fractions up with the A's and the B's differently, you might have got them in the other order, and that's fine. Anybody, as I was going around, everybody seemed to be doing great with these. So, great. This is the bulk of the work, but we should actually write out what this all means. It means that original thing is the same as the integral. So A is the one that goes above x minus 3. So x plus 3. So this should say minus 2 over x plus 3 and 5 over x minus 8, right? And then we do these integrals. Each of those is a ln of something or other. And those things that appear in the numerator are coefficients. So minus 2 ln absolute value x plus 3 and 5 ln absolute value x minus 8. There you go. With the plus c, of course. All right, this is the partial fractions trick. Any thoughts about that one? All right, I got one variation that I want to discuss. There are actually several variations of the partial fractions trick that I don't think we need to get into. One thing is, what are you supposed to do if the denominator, you factor the denominator into two factors, but I'm sure everybody knows, sometimes these things, when you factor, you get the same factor twice, but that actually screws this up. If I'm trying to do this, but the denominators are the same factor twice, then you wouldn't actually, when you add them together, you wouldn't need to do the common denominator even. Like, this whole process is messed up if there's the same denominator twice. But so I just want to say there is a trick for that. I don't really think it's worth spending our time on, but there are some extra technicalities that might arise when you do the partial fractions. And if you look in our book, you'll see they do more slightly fancier things. I want to talk about one, which is sort of like a more significant technicality. Let me just say this works with a quadratic in the bottom and up to a degree 1 in the numerator. Like what the example we just did had a degree 1 in the numerator. That was this right here, right? But you're going to say, you'll see actually there's another problem. If the numerator has degree more than 1, then when you make this common denominator thing, actually there's no way, if you had an x squared in the top here, there's no way these could add up to give you an x squared. And so this general technique will not work if the degree in the numerator is bigger than 1. So this is something to discuss. What if the numerator has degree bigger than 1? And there is another trick which we'll have to do in that case, and this one I think is worth discussing. So here is an example. Sorry, I mixed my papers up here. Here is an example. 3x squared plus 18 and x squared minus 5x plus 6. All right. So, like I said, you could try to do the same partial fractions trick, but those numerators, if you split it apart into the a and the b thing, equate the like terms. They will have an x term and a constant term, but they're never going to have an x squared term. And that is what's going to make that method just by itself is not going to succeed when you have an x squared term in the top. What we have to do is reduce the degree. Sorry, this is not the example that I wanted to do. I still have my papers mixed up. Can I postpone this one? I do want to talk about this example next. I wanted to do another one first. Sorry about that. Save that one for later. Not too much later, but how about this? I wanted to do an even bigger one. All right. This is one where the numerator has degree bigger than 1. Here the numerator is degree 3. All right. And there is a special trick for reducing or somehow simplifying this fraction so that the numerator always has degree less than the denominator. And this is something you may have seen before. We're going to do long division here. In this context, this is called polynomial long division. I'm going to do we're actually going to do the division, the thing on top divided by the thing on the bottom. And this is a little weird if you've never seen it before, but it's just like long division for numbers. So maybe let's just refresh our memory about how to do long division for numbers. So here's a little sidebar here. Long division for numbers, like if I want to do something like, I'm just making these numbers up, 8764 divided by 7. That's not very interesting. How about 2764? That'll be better. Sorry. All right. Can we do the long division here? I hope everybody remembers at least vaguely how to do long division with numbers. I would try to divide the 7 into the first digit here, but actually 2 is less than 7, so 7 doesn't go into 2. I'll take the first 2 digits. 7 going into 27, that would be 3 times, right? 3 times 7 is 21, which is, and you can't go another one. So I put 3 here, and then you multiply, so that's outside the box here, right? Then you multiply. 3 times 7 is 21, and I put that down there. Then we subtract. I hope you remember this from 4th grade or whenever you learn this. 27 minus 21 is 6, right? And then I bring down, and then I check, is the 6 less than the 7? Yes, it is. If it's not, then you didn't do it right. Then you bring down the next digit, which is a 6, and I repeat the process. So now I try to go 7 into 66. I believe that's 9. 9 times 7 is 63, so I put that here. Subtract, I get a 3. I bring down the next digit, is a 4. 7 into 34, that would be 4. And then 7 times 4 is 28. Subtract here and 6. And now you stop because you got to the end of the number. And in 4th grade, you write your answer as something like this R6, which is very strange. And after 4th grade, nobody ever wrote a number like that in your whole life. What does this actually mean? It means that there is like a leftover part after doing the division. And in this case, remainder of 6 really means a more sophisticated understanding of what that means. Really what it means is the answer is 394 plus 6/7, right? There's 6 bits left over when you try to do the division. And the bits that I'm talking about are sevenths, all right? That's what the remainder of 6 really means in a problem like that, all right? Anyway, let's try and do this, but I'm going to do it for those polynomials. This is a little weird if you've never seen this before. It does work exactly like ordinary division of numbers. So the numerator, the thing which is getting divided, goes inside of the little thing there, whatever that's called. And then the denominator goes on the outside, all right? And we are going to do this kind of digit by digit, where by digit I refer to the terms with each individual power. So you should start off by looking at sort of this thing into that thing. X squared dividing into 2x cubed. Another way of thinking about that is, what do I need to multiply x squared by to make it equal 2x cubed? And the answer is 2x. So I put 2x here. That's because if you divide 2x cubed divided by x squared and like cancel the powers or whatever, the answer is 2x. Another way to think about it is 2x is the thing you need in order to multiply 2x times x squared equals 2x cubed. It really is. All right? That was the first kind of like digit of the answer. And now, just like the long division, you do a multiplication. So I'm going to multiply 2x times this and write it down here. So 2x times this. In the first term, it becomes 2x cubed. But I'm going to do the whole thing. So also 2x times x, that's 2x squared. And then also 2x times negative 12 is negative 24x. All right? I am distributing 2x across the whole thing out there. I guess this is called the divisor, isn't it? Something like that. This is the dividend. I don't usually use words like that, but I think that's what they're called. All right? And now we put a little line here and subtract term by term. 2x cubed minus 2x cubed, they go away. That's 0, as it should be. X squared minus 2x squared is negative x squared. And then negative 23x minus negative 24x is positive 1x. All right, this can be a little confusing with the signs of everything, but I'm subtracting the top one minus the second one. All right? Okay, continue the division. Bring the next digit down, which we do as usual. That is the 16. Should come down here. And now I'm going to divide once more. This time I'm dividing this thing into here, right? Can anyone tell me what's the quotient in this digit? Yeah? Yeah, just -1. You want this term divided by that. So negative x squared divided by x squared. And the answer is just -1. So up there, I go -1. And now we repeat the procedure. So I multiply this digit, -1, times all of that business, and I write it down here. It's going to say, I like multiplying by -1, negative x squared, negative x plus 12, right? And we subtract. The negative x squareds cancel because I'm subtracting. Then in the next term, I have 1x minus -1x. This is 2x. And then 16 minus 12 is 4. And now we are done. This, how do you know you're done? It's because I'm trying to get a polynomial as the answer. And I got the constant term here. They're just like, there is no more terms of this polynomial. That right there is the remainder. So this is the quotient. That's sort of like the answer when I divide them. And this is the remainder. All right? So to write out my final answer, I'm going to try to write it kind of like this. I'm not going to use the R thing. Do it this way. So my final result of the division is, so 2x cubed plus x squared minus 23x plus 16 divided by x squared plus x minus 12. This is what I was doing when we did this division. What is the answer? The answer is 2x minus 1. And then plus some remainder piece, and that remainder would be 2x plus 4 divided by the original denominator, right? That's the remainder term. When you do this long division, you'll always get an answer part, the quotient, and then plus the remainder part. Although I suppose sometimes the remainder is 0. All right? And now you can see, how would we do this if we were doing integrals here? To do all of these integrals, well, on the right side now, we have 3 terms. The first 2 are easy to integrate, and this one, we can do partial fractions on it now. Partial fracs with an x. Because now this one has a lesser power on the top than on the bottom. And that was the whole reason we did the long division, was because the degree on top was bigger than on the bottom. And so, but after doing the long division, it is now of the appropriate form to do the partial fractions. All right? I don't want to do this. I have just one more example to do where we'll actually go through the entire thing, and that'll do us for today, if that's all right. Let's just try one more big example like this. These long division ones can take a while. And it's this one, the one I wrote down before, sorry, which I postponed until now. Let's try to do this integral by partial fractions, all right? We are going to do the partial fractions eventually, but we have to first do a long division because the numerator here is not of lesser degree. So we will first do long division, then the partial fractions. Partial fracs. All right? So let's do the division first. We got to set it up. Remember, which one goes on the inside? It's the top, yeah. As we said, right? It's the top, yeah. It's the top thing divided by the bottom thing. So the top thing goes on the inside. Now, since we're doing this kind of like digit by digit, actually it's important in an example like this to keep space for 0x in the middle, right? That's because when we do the long division, we must actually consider that middle digit. It's like a digit in the long division as a 0. All right, so hold space for the 0. And then outside, x squared minus 5x plus 6. All right? Let's do the division then. So we have to, I am comparing to begin with this term and this term. I want to do 3x squared divided by x squared. That's just 3. So the quotient in the first digit is 3. And then we multiply. It's going to be 3x squared minus 15x plus 18, right? That's distributing the 3 across the thing out there, the divisor. And then subtract. 3x squareds go away. I next have 0x minus negative 15x. The result is positive 15x. And then 18 minus 18 also cancels. You could say plus 0 if you like. All right? And this is the end of the division, right? We have already divided getting a constant term. There aren't any more terms of the answer because the answer is going to be a polynomial. And so that's the quotient, 3, and that's the remainder. It's just 15x. All right? So having done the long division, we can say what I started with is the same as 3, that's the quotient, plus the remainder part, 15x over x squared minus 5x plus 6. All right? I forgot my dx's. All right? So this is progress towards the final answer. And now how do we actually do, doing the integral of 3 will be 3x, so no problem there. The other part, that fraction, we do the partial fractions. So here, let's do the partial fractions. PFs. I got my PFs. It's going to be the usual thing. We do the A's and the B's, right? So it'll say 15x over x squared minus 5x plus 6 equals A over the factors here. Minus 5x plus 6, I think the factors will be negative 2, x minus 2, and x minus 3. So I want A over x minus 2, B over x minus 3. That's the order I'll do them in. All right. Do our common denominator thing. Here it'll say A x minus 3 plus B x minus 2 over this business. And then we equate the two numerators. So 15x equals, I'll rearrange the stuff over here, a plus b x, and then plus negative 3a minus 2b. And so for the partial fractions, my system shall be a plus b equals 15, and minus 3a minus 2b equals, what is that one?
Just 0?
Yeah, it's 0. There's no constant on the left side, so when I equate the like terms, I imagine a plus 0 on the left side to equal the constant. Yeah, great. Okay, and then solve the system by whatever means you like. How about if I add 2 times the first equation to the second one? It will cancel the b's. Adding 2 times the first equation to the second one, that will say negative a, no b's, and then equals 30. I think that's what you'll get if you do 2 times the first one plus the second one. The b's cancel. So a is negative 30, and then a plus b is 15. So that means negative 30 plus b equals 15. B is 45. All right. So these are our constants. Right, we're pretty much done at this point. We just have to sort of remember where we came from and where we're going here. This is where we were at, and then I just did the partial fraction. So this right here will continue. So that is the same as, okay, I didn't do anything to the 3, but I split apart that fraction where a is negative 30, and that's the one that goes on top of x minus 2. So negative 30 over x minus 2, and then 45 over x minus 3. All right, and this is the fully sort of unwound version. The division gives us the 3 part, and then the partial fractions gives us that stuff. And then what's the integral? So the 3 is 3x, and the other 2 are logs. Minus 30 ln x minus 2 plus 45 ln x minus 3. That's how we do it. This is the partial fractions with a long division. All right. I think that'll do it for today. Thank you for your attention. I was right before the break. You'll have some practice please on the homeworks. Have a good little break. See you next week.